Hi, I'm Lauren from CK-12 Foundation. I work on the science content team, and today I wanted to talk to you about a very important topic in science, and I wanted to start with a question. This question is, what conditions would cause a cell to lose or gain too much water? And in order to understand this question better, I want you to think about this question as we go through a lesson and a demonstration using a model. The model that I'm going to use today is in the form of a raw chicken egg. The raw chicken egg is a great demonstration to use. And again, this is a demo. I wouldn't recommend doing this at home, but under the supervision of a teacher in your classroom because there are some safety concerns. But with this raw chicken egg, what I did was I placed it in vinegar for 24 hours to actually remove the shell. After I removed the shell, what was intact lying just beneath that shell was a membrane. And this is going to represent a cell because all of our cells inside of us have a cell membrane. And that cell membrane helps regulate things that move into and out of the cell. And so thinking back to that question, I actually placed, after I removed my shell, the eggs in different solutions. One of the solutions, which I'm going to show you the results in a little bit, was water, and the other solution was maple syrup. And so I want you to keep thinking about that question that I asked you and thinking about those two solutions and what you think would happen to those cells. Do you think the model of our cell is going to gain water or lose water if we placed it in water itself, or gain water or lose water if we placed it in maple syrup? And the why behind that, to explain that, is really key and important here. So I want you to be able to do that by the end of this lesson. All right, so to help us really understand this better, I am going to share my screen with you and hop on the CK-12 website to the Life Science Flexbook, to a diffusion lesson. And hopefully you can see my screen here. And this link is on the YouTube page below if you want to visit this later, that I recommend for a great lesson on diffusion. This picture here is very interesting, I think, and it has a great question to start. What happens if you put a few drops of food coloring in water? So maybe you have experienced seeing this before. As you can see, the food coloring is beginning to disperse throughout the liquid in this flask here. And eventually over time, you'll start to see that food coloring disperse uniformly throughout this liquid. That happens through a process known as diffusion. Diffusion actually, by definition, is a process where molecules move from a higher concentration to a lower concentration. That higher concentration being those few food drops that we had dropped initially in there, and the lower concentration, how it diffused throughout the liquid in this container. And this diffusion process is extremely important in cells. It's a very important cellular process that happens. And what I wanted to focus on was a special type of diffusion known as osmosis. This is with respect to the diffusion of water. And the diffusion of water is critical because our cells have inside it and surrounding it water all the time, but not just water. There's also solutes dissolved within that water inside and outside the cell. And what's important is our cells want to maintain a balance of water. They don't want drastic changes in it. However, our environments inside and outside of our cell are constantly changing. So our cells are having to find ways to regulate that. So I'm going to scroll down this lesson here on the Life Science Flexbook page, and there's a great description about osmosis and some 3 different solutions or environments that we find ourselves in that the cell has to regulate osmosis with respect to if they're in one of these. And I wanted to walk through these with you. These are very difficult terms. If you've taken biology or might take biology soon, these are very difficult terms that you will be introduced to. So I'm going to do a new share now with you and share my whiteboard that has some of these descriptions already set for us and some visuals to help us understand this better. Let's start by just saying these are beakers of water with solutes dissolved in them. These are the solutes, these gray dots here, and here are our cells. And so the first example here, hypotonic, I'm going to use my drawing tool. Hypotonic And hypo actually means less than. That's talking about the amount of solute within that environment. In a hypotonic environment, a hypotonic solution, there is actually less solute. And what that tells us is there's going to be more water concentration compared to inside the cell. So I'm going to put an H here for higher water concentration and an L here for lower. And what we know about osmosis, the diffusion of water, is that water actually moves from higher concentration to lower concentration across our cell membrane. So water is going to move from high to low inside the cell. And in this case, in this environment, our cell is going to swell. And if left in this environment for too long, it may even burst. This is not a good place for our cells to be in. So another type of solution or environment that we find our cells in is hypertonic solution. Hyper actually means greater than, and that's also referring to the amount of solute within the environment. As you can see, the beaker here has more solutes compared to inside the cell. So again, I'm going to put an H here for higher concentration of water versus lower concentration of water outside the cell. And again, by the process of osmosis, water moves from high to low, from inside the cell to outside the cell. And in this case, our cell is going to shrink and shrivel. Not a good place for our cells to be in. It can be very dangerous. A good example of this is if you've ever heard someone tell you that it's dangerous to drink ocean water, it's because of this fact that the ocean water is hypertonic to our cells. And then finally, we have isotonic. Isotonic environments, iso means the same or equal. There are equal amounts of solute inside and outside the cell here. And what that's going to tell us is water is going to continue to move. So I'm going to do a double arrow here. But there's going to be no net gain. That cell size is going to stay the same. And so isotonic, this state of equilibrium, is really important for our cells to be in. Again, though, can't always be reached and maintained because of the fact that our environment inside and outside our cell are constantly changing. All right, so we have those hypotonic, hypertonic, and isotonic environments in our minds right now. Let's go back. I'm going to stop sharing my screen now and go back to our demonstration and our model of our cell with the raw egg. And so I'll show you first the egg that I had placed in water after removing the shell. And you can see the size, much, much greater. We definitely have our cell that has swelled and increased in size. If I left it in longer, I bet it would swell even more. So what does this tell me? Just from simply observing it, water definitely entered my cell here. And in that case, if you think back to those environments, hypotonic solution was what I placed my cell in. The water was hypotonic to my cell. Water entered the cell from high concentration to lower concentration. And that makes sense, right? Our cells, just like our egg here, our model cell, is actually not just water, but has a lot of different solutes dissolved into it as well. So I'm gonna put that down and let me show you now. I had some really drastic changes with my cell when I placed my cell in maple syrup. Try to not get too distracted by the color change, but I did see a color change, but I definitely saw a change in the size of my cell. It's shriveling here. Definitely the water had left the cell. The size of it is definitely reduced. I can definitely see some of the concaving of the cell here, of that membrane. And what that tells me, if water left the cell, the maple syrup likely was a hypertonic environment, representing a hypertonic environment. So water moved from high concentration inside the cell to lower concentrations outside the cell, really decreasing that size of the cell. Again, not a good place, a dangerous place for our cells to be in for too long. So hopefully you get a better sense of osmosis and some of the environments that we find ourselves in. But did you know that diffusion doesn't just happen in liquids, it also happens in gases. And this sometimes is really difficult to model and to see. But CK-12 actually has a great model of this through a simulation called Speedy Smells that I wanted to walk through with you today. The link for this is in the YouTube page below, so I encourage you to visit that. And I'm going to share my screen again with you to show you that simulation. This is one of many that we have on the CK-12 website. This is the one from chemistry. And here's a big question here. Why do we smell some things before we smell others? And we've all experienced this before. Even though we can't maybe see gas molecules, maybe they're not visible to us, we have sensed it through smell. Think about a time when you maybe visited a friend's house and you entered their home and you smelled something from the kitchen. Maybe they were baking cookies. How did that smell diffuse, right, from the kitchen to you while you entered the house? And I gave it away. It actually diffused by diffusion. So gases can do this too. And so this simulation does a great job in testing different items for you. And I'm going to show you now this experimental setup. You can really just test various smelly items, they call it, at the bottom here. For fish, we can maybe even test perfume. And what you have is you can test them at the same time. And you'll notice there's some information given about them in terms of molecular mass, because the mass of these molecules is really responsible for the object's smell and really how quickly that they will diffuse across a space. And in the case here, this individual is going to be our tester who's going to sense one of these before the other. Before I start the simulation, wanted to make a prediction, thinking about what you might have some prior knowledge about and maybe your understanding of molecular masses and which one you think will diffuse across the room quicker for this individual to sense. And so we're going to test this now through our speedy smell simulation. And you'll notice, although we can't usually see gas molecules of any kind diffusing through the room, the simulation is showing that in real time here. And our individual is going to hopefully sense one of these before the other. And looks like it's going to be the fish, followed by the perfume. And note that the fish molecular mass is less. So it looks like that molecular mass might make a difference, although you can test that with other items in this simulation to see if that holds. And notice too that diffusion is continuing as the molecules are leaving that higher concentration where the source is across the room and diffusing across the room to lower concentrations, just like we would have in that liquid form, just a little different here. Oftentimes too, gases move a little quicker. Some other real world context. So I encourage you to visit this and explore some other items to test. There is some real world examples that follow all of our simulations. Here's a few of them here. Like for instance, I really like this one. Why do onions make us cry? If you've ever cut an onion and your eyes have cried, it's the result of diffusion of molecules leaving those onions. So it goes through a nice explanation about that and other examples too. All right, well, we are running out of time. So I just wanted to wrap up by saying I hope you learned a lot about diffusion and the process of osmosis, a form of diffusion with water within cells, and also relating that to gases. I encourage you to visit us tomorrow for CK-12 Live with Monique, one of our content member team members will be going over reflections. All right, well, thank you again for joining me. Have a great day. Be safe. Take care.